Assalamu alaikum. My name is Shachil, and the topic that I chose for my presentation is the discovery of parity violation. And I will be discussing the parity, what parity is, what this parity symmetry is, symmetry principle, and I will be talking about the handedness of the coordinate systems and how it led to the discovery of parity violation. First of all, I'm really sorry on my part that I had internet issues and I couldn't answer all of those questions and I couldn't present my presentation as well. So really sorry on my part, and let's just get straight into the presentation. So let me start with the historical background, and I will just give a few information about where it all started and how it went on and led to the discovery of the parity violation. So it all started in 1896 when Becquerel discovered the radioactivity. After that, in 1899, Rutherford discovered the beta decay. He called the less penetrating rays the alpha decay and the more penetrating rays the beta decay. In 1909, Rutherford called the alpha particle as the helium nuclei. In 1911, he bombarded the gold foil with the alpha particles and found out that there was a nucleus inside the atom. In 1928, Gamow, Kearney, and Condon gave the theory of alpha radioactivity. Later on, in 1930, Pauli gave the neutrino hypothesis. In 1932, Andreessen discovered the positron, and in 1932, Chadwick discovered the neutron. And then in 1934, Enrico Fermi gave the theory of beta radioactivity. In 1956, T.D. Lee, Yang, and Wu discovered the gravity violation and weak interaction. In beta decay, T.D. Lee, Yang, and his team was the one to find out about the parity violation, and Wu was the one who did the experiment. And we will also discuss the Wu experiment in the later slides. So let's start with the parity symmetry. What is parity? Parity is a mathematical operation which simply flips sign of coordinate axis. For example, if we are working in a xyz plane, so the x will shift to the minus x and y will shift to the minus y, and z goes to minus z. I mean, the axes are all inverted and we move from the right-handed system to a left-handed system. So if we take the position vector r, it moves to the minus r. So those quantities which change signs under the parity operation, those are known as the true or polar vectors. However, there are few quantities which, when parity operation is applied on it, does not change sign. For example, Newton's second law, F is equal to ma. When parity operation is applied on it, it does not change signs, which means that it cannot differentiate between the left-handed system and the right-handed system. And there are other laws like the laws of gravitation, Maxwell equation. They are all invariant under the parity transformation. This means that they will lead to evolution of physical events which can be used to distinguish whether or not you are in the left-handed system or in the right-handed system. Mm, That means that the universe is unable to distinguish between the left and right. That is, the universe is symmetric with respect to right and left. It was considered before the discovery of the parity violation. So those quantities which are invariant under the parity transformation, these are known as the pseudo or axial vectors. Here is a diagram showing the parity symmetry. That is, parity symmetry can also be visualized in the form of a mirror images. For example, when we stand in front of a mirror, our right hand in the mirror we see it as a left hand, and when we move our left hand in the mirror we see our left hand moving. So that is how we can visualize the parities. In the same way, if we see the picture here, so if we have a point in the xyz axis, so if we apply parity on it, it will move to minus x minus y and minus z. So Whenever we study any physical phenomena, we study it with reference to some coordinate axis. So we can just categorize them as the left-handed coordinate system or a right-handed coordinate system. So this is how a left-handed coordinate system would look, and this is how a right-handed coordinate system would look. So how we can actually know if a system is right-handed or a left-handed system? If we take our right hand, this is my right, so yes. So if we take our right hand and we curl our fingers in the direction of the spin of the particle, and our thumb points in the direction of the particle, direction of motion of the particle, then it's a right-handed system. However, if the direction of the particle is in the left side, if we use our left hand and we curve our finger in the direction of the spin of the particle and our thumb points out in the direction of the particle, then it's a left-handed system. And what examples do we find in real life? For example, if there are electrons are either left-handed and right-handed, and photons are can also be left circularly polarized or right circularly polarized. But when they looked into the neutrinos, they only find the left-handed neutrinos and right-handed antineutrinos. They did the experiment on the cobalt-60 and they found out this was the observation. So that led to the discovery of parity violation. If the parity was conserved, they had found the left-handed neutrinos and the right-handed neutrinos as well, and right-handed antineutrinos and left-handed antineutrinos as well. But that was not the case. They only found the left-handed neutrinos and right-handed antineutrinos, which led to the violation of parity. So I guess this answers the question of how they find out the about the parity is violated or not. Breakdown of parity symmetry. What led to the breakdown of the parity symmetry? So, according to symmetry principle, the universe cannot distinguish between the left and the right-handed systems. So I gave the examples, that is Newton's second law cannot differentiate between the if we are working in the left-handed coordinate system or in the right-handed coordinate system. Herman said that a thing is symmetrical if there is something we can do to it so that after we have done it, it looks the same as it did before. For example, let me give you an example. How can I give an example? For example, there is a word, say mem, M-A-M-M. So if we apply parity to it, that is, it will go from, if we write it oppositely, M-A-M, this will say the same. So that is how we can define parity in simple terms. In 1924, Oliport discovered the even and odd energy levels. He discovered them while he was observing the structure of spectrum of iron. He called those stroked and unstroked energy levels. He didn't have any explanation for this until 1927. Eugene Wigner found out that these energy levels can be defined using the parity operation on the Schrödinger wave equation. So Eugene Wigner was the one who formalized the principle of parity. In 1956, T.D. Lee, C.N. Yang and his team find out that there was no work being done on the beta decay and parity, and there was a theta pi puzzle going on at that time. Theta tau puzzle was going on that time. They were the same particle. I mean, they had the same spin, same masses, and same lifetimes, but they decayed into two different particles. For example, tau decayed to 3 pi mesons, and theta decays to 2 pi mesons. Actually, it was 2. I don't know how it is not edited. So that's a mistake on my part. Let me correct it. So it's a 2 there, 2 pi mesons. So we also know those particles at the K mesons today. So they were working and they find out that they are the same particle and they decay into different particle. How is that even possible? So we thought maybe it is parity. They are not invariant under the parity operations. So they published it, that is if parity is violated or not, and they did search for the literature and they couldn't find anything. So they asked mm, who to do experiments on it, and they did experiments on it. I will discuss the Wu experiment in the next slide. So what was actually the Wu experiment? Wu experimented on the cobalt 60, which decayed to nickel, gave electron and a antineutrino. I mean, nickel was in the excited state, and so when it returned to normal state, it released the photons. So cobalt 60 converts to a nickel, electron, antineutrino, and a photon. So what is actually happening is neutron from a cobalt is converted to proton, which is present inside the nickel right now, and an electron and an antineutrino. So this is the beta negative decay. So if we talk about the neutrino is made up of up, down, down quark, and a proton is made up of up, up, down quark. So what is actually happening is a down quark is converted into a up quark, giving away the electron and the antineutrino. So what they did and Wu experiment, how they did it, they applied the magnetic field to align the spin of the cobalt, and they observed the emission of the electron, and they thought if we want to apply parity on it, if they want to check the parity, they just reverse the magnetic field. So the spin was reversed, and they checked the emission of the electron, if the emission was along or opposite to that of the cobalt 60. So there can be two scenarios. One scenario can be the spin of the electron is op opposite to that of electron, or the spin of the electron may be in the along the cobalt 60. So in, before in slide number I guess 3, I explained the handedness of the system, and I told you that right-handed electron can be either left-handed or right-handed, and photons can be either left circularly polarized or right circularly polarized. But when they did the experiment, they found that there are only left-handed neutrinos and the right-handed antineutrinos. They couldn't find a single left-handed antineutrino, which means that scenario 2, which is not possible. I mean, it is not possible. These two scenarios are both possible energetically, and they obey all the laws of the physics, but they couldn't find a single left-handed antineutrino. So that is how they knew that it was not possible. Whose experiment? They observed that the 70% of the beta particles were emitted opposite to the nuclear spin. So ma'am asked me the what is the meaning of the polarized cobalt beta decay. So polarized means that they applied the magnetic field and the spin of the cobalt 60 was aligned with that magnetic field. So this is what meant by the polarized. And I guess ma'am asked later in which I couldn't answer it before the meeting because the meeting was ended. It was what is meant by the A exponential and A parity. It is I tried to find it, but I couldn't because I checked a paper in which they explained all the process, and it was like they were just explaining their conversation, what they had with each other and everything, but I didn't find what the A was, except for I had just an idea that it meant the asymmetric distribution. Result of the experiment, I mean, they did the experiment later and they showed that the parity is actually violated. So they showed that the in parity reflector experiment, the electrons are emitted preferentially along rather than opposite to the direction of the magnetic field. So that is how they knew about the violation of parity in the beta decay. In the gravitational, electromagnetic, and strong interaction, we cannot distinguish between the left and the right-handed coordinate system. That is, there is no preferential direction. But in case of the weak interaction, there is particular preference towards a particular handedness. So when we actually talk about this is that the universe Parity's matrix said that the universe cannot distinguish between the left and the right coordinate system. But Parity's violation says that the universe can distinguish between the left and the right. So what is actually the reasons behind the what and left-handed neutrino and right-handed antineutrino? This has something to do with the quarks. I mean, quark has the left and right hand side. They oscillate between both. Only one of these sides participate in the beta decay. So from this we can say that the universe can distinguish between what is left and what is right. So oh, from this we can only say that the only weak interaction is responsible for the transformation of quarks. Quarks do not change identity due to other interactions like electromagnetic interactions or strong or gravitational interactions. So I hope so it answered the question of Ramin that how we find out that the parity is violated. We find out through the neutrinos and antineutrinos, because when they did the experiment they find out that the antineutrinos are always right-handed and neutrinos are always left-handed. However, if the parity was conserved, they could have find out the left and right-handed neutrinos and left and right-handed antineutrinos, just as they have the right and left-handed electrons and left and right circularly polarized photons. But they only find the right-handed antineutrinos and left-handed neutrinos. So that is how they find about the parity is violated in beta decay. And ma'am, I guess I have asked your questions as well, and there was no questions, ma'am. Really sorry on my part that I don't know what happened today about to my internet. It was working quite well, but I'm really sorry for that. Thank you so much. And if you have any questions, I'm always there to answer all of those. Thank you so much. That's all from my part, and I'm really sorry for the inconvenience. I was so much into this presentation as it was my one presentation, and I was really hoping that it goes well, but they say you can't just deal with everything. We have our good days and bad days, so I guess it was my bad day, and I'm really sorry for everything. And I guess I answered the questions, and if anyone have other questions, I'm always there to answer those. Thank you so much, and I'm sorry again. Thank you.